right now, millions of developers are basically forcing their users to download a really heavy chunk of code just to teach a web browser how to do something it actually already knows how to do.
Yeah, which sounds completely absurd when you put it like that.
It really does. But it happens every single day in code bases all over the world. So, welcome to this deep dive. If you are building digital products or, managing a development team or even just fascinated by how the internet actually works under the hood, we have a mission for you today.
Right, and that mission really boils down to one concept: trusting the platform.
Exactly.
Which means realizing that the environment you are building in, the modern web browser, is essentially this highly sophisticated operating system. I mean, it is hiding massive optimized power right beneath the surface.
Yeah, and when developers ignore that native power, they usually just end up reinventing the wheel and usually doing it pretty badly.
Oh, definitely.
So, to explore this, we are looking at a fantastic narrative piece by software engineer and tech writer Aaron Rose. It is called The Secret Life of JavaScript, the Compressor, and it was published over on tech-reader.blog.
I really love this piece because instead of just giving us a dry technical manual, Rose frames this whole performance bottleneck through a story.
Right, it is super engaging. He introduces us to two engineers. There is Margaret, who is this seasoned veteran, and Timothy, her junior colleague.
And the setting Rose creates is just brilliant. They are working in this grand Victorian library in London.
Oh, yeah, the atmosphere is great.
It immediately establishes this vibe where craftsmanship really matters. They aren't just hacking features together to meet a quick deadline.
Yeah.
They're supposed to be thinking deeply about the architecture and the actual quality of what they are building.
But despite that really high-minded environment, Timothy is currently in the trenches. He is dealing with a highly relatable nightmare.
We have all been there.
We really have. He is staring at his DevTools network tab, and he is just watching this progress bar crawl at an absolute snail's pace.
Right, because he is building a diagnostic tool for their application.
Yeah. Basically, when something goes wrong on the user's end, the app gathers local diagnostic logs and uploads them back to the server so the engineering team can analyze them.
The intention is great, obviously.
Totally.
But the execution is hitting a massive wall because of the sheer volume of data. I mean, these aren't tiny little error codes. Timothy's trying to upload 15 megabyte plain text log files.
Which is huge for text. If your user happens to be on, say, a spotty 3G cellular connection or even just bad hotel Wi-Fi, uploading 15 megabytes of raw text feels like it takes a lifetime.
It basically paralyzes that specific user interaction, yeah.
So Timothy correctly identifies the bottleneck. The payload is just way too big. And he reaches for a very standard, modern developer solution.
Right.
He goes out and imports a third-party zipping library to compress those text files before they ever leave the browser.
He brings in what we call a polyfill. Essentially, it is a piece of code that provides functionality you assume the browser lacks.
Right, exactly.
In this case, he imports a 45 kilobyte JavaScript library to handle the data compression. And, on paper, it seems perfectly logical. Shrink the file, speed up the upload.
But here's where we really need to look at the mechanics of what is actually happening. Because a 45 kilobyte library might sound tiny when we are all used to downloading gigabytes of video.
Yeah, 45 kilobytes is nothing in video terms.
Right. But in the context of JavaScript executing in a browser, 45 kilobytes of dense algorithmic code is a massive liability.
It really is.
It is not just the time it takes to download that library over the network. It is the cost of parsing, compiling, and ultimately executing that code.
And compression is incredibly CPU intensive.
Totally.
I mean, it requires heavy, complex mathematical calculations to scan through millions of characters, find patterns, and shrink them down. And because JavaScript is traditionally a single-threaded language, all of that intense math is forced to run right on the main thread.
Okay, let's unpack this with a visual, because the distinction between a network bottleneck and a CPU bottleneck is just crucial here.
Sure.
Imagine you have a giant king-size mattress, and you need to shove it through a tiny, narrow doorway. The uncompressed mattress is your 15 megabyte plain text file, and the tiny door is your user's slow network connection.
You obviously can't shove it through as is.
Right. So Timothy's solution is to buy a heavy-duty industrial trash compactor to crush the mattress down so it fits through the door.
And that trash compactor is the 45 kilobyte JavaScript zipping library.
Exactly. But here is the major architectural flaw. The compactor itself is so incredibly massive and clunky that the moment you assemble it inside your house, it completely blocks the main hallway.
Oh, wow. Yeah.
Nobody can get past it to the kitchen, nobody can get to the living room.
And the main hallway is the browser's main thread.
Yes, when the main thread is blocked by this heavy JavaScript math, the entire user interface, the UI, just freezes. The user tries to click a button, nothing happens. They try to scroll the page, and it is locked.
That is frustrating.
So yes, you eventually crush the mattress and get it out the door, but you have completely paralyzed the entire house in the process. You traded a slow network upload for a totally frozen application.
Which is a terrible trade-off.
Truly awful.
And Aaron Rose highlights this beautifully in the story when Margaret, the senior engineer, walks over with her morning dark roast coffee and just looks at Timothy's code.
I love how she handles this.
Yeah, she doesn't just tell him he is wrong. She uses the Socratic method to lead him to a realization.
Right.
She asks him to think about how their web server delivers their main JavaScript and CSS bundles to the browser in the first place.
Which Timothy knows. He knows the basics of web infrastructure. So he says, well, the server compresses our code using gzip, sends it over the wire, and then the browser decompresses it on the fly the second it arrives.
What's fascinating here is the logic trap Margaret sets up. Timothy admits that the browser is already decompressing code seamlessly. So Margaret points out the really obvious conclusion. If the browser can decompress incoming code, the JavaScript engine inherently possesses a native, deeply integrated understanding of the gzip algorithm.
I mean, the browser already knows how to zip and unzip data. It has to. The entire modern web relies on that capability to function at scale.
Exactly. Which leads to Margaret's mic drop question for Timothy.
Oh, let's hear it.
She asks, if the JavaScript engine already has this highly optimized compression engine baked into its core, why are you forcing the user to download a 45 kilobyte JavaScript polyfill just to teach the browser how to do something it already inherently knows how to do?
It is such a brilliant question. I mean, why bring a giant trash compactor into the hallway when the house was built with a highly efficient, invisible compactor hidden inside the walls?
Exactly.
But wait, if this native compression engine is so powerful and it is already sitting there inside Chrome and Firefox and Safari, why are we only talking about this now?
That is a very fair point.
Like, if I'm a developer listening to this, my natural pushback is, why haven't we been using this native engine for the last 10 years? Why did Timothy and millions of real-world developers instinctively reach for a third-party library?
It is absolutely the right question to ask. And the reality is, for a very long time, developers literally couldn't use it.
Really?
Yeah. The browser's internal compression engine was walled off. It was treated strictly as an internal networking tool.
Oh, I see.
The browser used gzip for its own logistics, fetching HTML, CSS, and JS bundles, but it did not expose an API that allowed developers to route their own custom application data through that engine.
So the engine was running, but developers just weren't given the keys to drive it.
That is the history of web development in a nutshell, honestly.
Oh, wow.
Browsers historically kept their most powerful, low-level capabilities locked away for security and stability reasons.
That makes sense.
So if you wanted to compress user-generated data on the client side, your only option was to build or import a JavaScript polyfill that replicated that math from scratch, right on the main thread.
But the article makes it really clear that the landscape has shifted. Margaret goes to the whiteboard to show Timothy that the walled garden has doors now.
Yes, it does.
And the specific key to those doors is something called the Streams API.
Right. The Streams API represents a fundamental shift in how browsers process data. Margaret writes down two specific native interfaces on her whiteboard, compression stream and decompression stream.
Okay.
And these aren't third-party libraries. These are built directly into the modern web platform.
Let's break down how this actually bypasses the bottleneck, because understanding the mechanism here is what makes this so powerful.
Definitely.
Timothy's flawed polyfill tried to swallow the entire 15-megabyte text file at once. It loaded all that data into the JavaScript memory heap, ran heavy math across the whole thing simultaneously, and triggered massive garbage collection pauses.
Which is exactly why the UI froze.
Right. The Streams API, by its very definition, doesn't do that. It operates in continuous chunks.
Chunking is the secret sauce here. Instead of allocating memory for a massive 15-megabyte block, a stream takes a tiny, manageable piece of the data, processes it, hands it off, and then immediately moves to the next piece.
So what does this all mean? Let's map this back to our visual analogies. Earlier, we had the giant mattress, but let's look at it through the lens of eating.
Okay, I like where this is going.
Using a synchronous JavaScript polyfill to compress a massive file is like trying to shove an entire extra large pizza into your mouth in one single bite.
That sounds painful.
It is. It is synchronous blocking. You physically can't do anything else. You can't breathe. You can't talk. You just choke until the bite is finally swallowed.
Which is your frozen UI.
Exactly. But utilizing the Streams API is like putting that pizza on an efficient, continuous conveyor belt that feeds you manageable, bite-sized slices one by one.
That is a great way to picture it.
Yeah, you process one slice, swallow it, and the next one arrives. You never choke. The system just keeps humming along.
The conveyor belt analogy is perfect for streams. But, the architectural triumph of compression stream isn't just that it chunks the data. It's actually where the data gets processed.
Oh, really?
Yeah. When Timothy used his JavaScript library, the V8 JavaScript engine had to do all the math. When you use the native Streams API, you are fundamentally leaving JavaScript behind entirely.
Wow, okay. So you are offloading the work to the browser's foundation.
Exactly. Browsers are built using really fast, heavily optimized, low-level languages like C++ or Rust.
Right.
The native compression stream is just a set of C++ bindings. So when you pass your data into this stream, the browser hands the heavy mathematical lifting entirely over to that native backend.
Ah, so the JavaScript event loop is suddenly freed up?
Yes. It just orchestrates the stream while the C++ engine does the actual crushing in the background, completely asynchronously.
Meaning the main hallway stays totally clear. The user can keep scrolling, clicking, and interacting with the app, completely unaware that a massive 15-megabyte file is being crushed down in the background.
And you even get choices on how it's crushed.
Yeah.
Aaron Rose's piece points out that developers aren't just limited to the standard gzip algorithm anymore.
Oh, that's right.
The native API also supports Brotli.
Which is a really crucial detail for text compression. gzip is fantastic, obviously. It uses algorithms that are highly efficient at finding repetitive patterns, which makes it great for code.
Right.
But Brotli, which was developed by Google, actually includes a pre-built dictionary of common web terms and phrases natively baked into the algorithm.
That is so clever.
It really is. When you are compressing plain text logs, Brotli can often achieve a significantly denser compression ratio than gzip.
So you are getting smaller payloads, faster execution, and absolutely zero UI blocking. I mean, it is a trifecta of performance.
Which brings us back to Timothy in the library. He has had the Socratic epiphany. He understands the mechanics of the event loop and the native C++ engine.
Yeah.
So now we get to see him actually implement this. And the first step he takes is arguably the most satisfying thing any software engineer can do.
Oh, absolutely. He deletes code.
Yes.
He strips out that entire 45 kilobyte third-party polyfill. He removes the dependency completely.
Goodbye, giant trash compactor.
Exactly. Then he rewrites his function using the native platform. He takes his massive 15-megabyte raw text payload and converts it into a readable stream.
Okay.
Once it is in that format, he uses a native method called pipe-through.
I just love the naming convention there. Pipe through. It instantly communicates what is happening to the data.
It creates a literal pipeline.
Yeah.
He takes the raw stream, uses pipe-through, to push it into the native compression stream specifying Brotli or gzip, and then funnels that newly compressed output directly into his fetch request to send it off to the server.
The narrative also highlights a vital best practice here, which I am glad Rose included. Timothy wraps his entire pipeline in a standard try-catch block.
Oh, you have to.
Yeah, when you are dealing with asynchronous data streams leaving the browser and traveling over unpredictable networks, things will inevitably drop. Packets get lost, connections just fail.
Right. Having production-grade error handling is non-negotiable. If the stream breaks halfway through, the try-catch block ensures the application knows how to fail gracefully rather than just throwing an unhandled exception and crashing the user's tab.
So Timothy finishes the implementation, he saves the file, the code is modern, clean, and totally dependency-free.
Beautiful.
Then he runs the ultimate stress test, he opens his developer tools, and deliberately throttles his own network connection to simulate that slow, spotty 3G cellular network that was causing the agonizing progress bar in the first place.
A real test.
Right. And he hits the upload button.
And the results are just transformative.
It is night and day. First, the UI remains buttery smooth, no freezing, no blocked main thread. Second, the user isn't downloading a massive polyfill just to use the feature.
And the upload itself.
It finishes in milliseconds. The native C++ engine quietly chunked the 15 megabytes, crushed it into a tiny fraction of its original size, and streamed it right over the wire.
It is a massive win. But, Margaret does step in to point out one crucial catch.
Right.
And we absolutely have to cover this because if you try to implement this native streaming trick today,
Right.
it will completely fail if you ignore the server side.
Yeah, because communication is a two-way street. The browser is now sending a tightly compressed Brotli or gzip stream.
Right.
If the server on the receiving end is configured to expect plain, readable text, it is going to receive this dense, compressed binary payload and have absolutely no idea what to do with it.
The backend will just throw an error because it looks like pure gibberish.
Exactly. The server has to be taught how to catch what the browser is throwing.
Fortunately, Margaret notes that setting this up on modern backend infrastructure is usually very straightforward.
Oh.
Yeah, if your team is using Node.js frameworks like Express or Fastify or Python frameworks or Go, handling compressed incoming payloads is often just a matter of flipping on a simple middleware flag.
Oh, that's easy.
It really is.
You essentially just tell your server infrastructure, hey, check the headers on incoming requests. If you see a header indicating the payload is compressed with Brotli or gzip, route it through your own native decompression middleware before you try to parse the body.
Yeah. It is a simple configuration change, but, if you forget it, the entire pipeline shatters.
It requires a holistic view of the architecture. You really have to understand both ends of the pipe.
Absolutely.
Here's where it gets really interesting, though. Taking a step back from the specific syntax, what makes Aaron Rose's piece so compelling is the broader philosophy it represents.
Totally agree.
This isn't just a tutorial on how to use compression stream. It is a lesson in unlearning bad habits. Timothy had to abandon his core assumption that complex problems require complex external solutions.
He had to let go of the reflex to instantly open his terminal and type npm install the second he hit a roadblock.
Yes. By letting go of that reflex and embracing the concept of trusting the platform, Timothy achieved something incredibly rare in software engineering.
What's that?
Well, usually, performance optimization is a game of trade-offs. If you want faster uploads, you add a heavy compression library, which hurts your initial load time.
Right.
If you want a smaller initial load time, you remove the library, which hurts your upload speeds. You are constantly pulling a blanket over your head, only to expose your feet.
I see what you mean. But by leveraging native APIs, you bypass the trade-off entirely.
Exactly.
Timothy achieved lightning-fast, unblocked background uploads, and simultaneously reduced the footprint of his main JavaScript bundle. He made the application significantly more powerful by deleting code.
That is the ultimate goal of trusting the platform. It
Yeah.
shifts your entire perspective as a developer.
It really does.
Instead of asking, what external tool can I download to fix this? You start asking, what tool am I already holding?
Because the modern browser is an incredibly rich ecosystem.
It is huge.
The APIs available today for, audio processing, video rendering, local storage, and complex mathematical calculations, they would have required massive external libraries just a few years ago.
So if you take one thing away from our deep dive today, let it be this. Before you instinctively reach for a heavy, complex, third-party dependency to solve a problem, take a breath.
Just pause for a second.
Right. Go check the documentation on MDN. Look at the current state of native web APIs. You might find that the browser has been quietly waiting for you to hand over the keys.
You could delete thousands of lines of code and make your digital product run smoother than you ever thought possible.
The platform is a lot smarter than we usually give it credit for.
It really is.
And that leaves us with a final thought for you to chew on as you step back into your own projects. We just explored how incredibly efficient the native Streams API is at asynchronously chunking and processing data that is leaving the browser.
Right. And how it entirely bypasses the JavaScript event loop.
Which naturally makes you wonder what else is sitting there.
Oh, absolutely.
Exactly. Since we know the browser is hiding all these optimized C++ engines under the hood, what other massive data-heavy operations are you currently relying on clinky polyfills for?
That is a great question to ask.
Think about complex image manipulation on the client side, resizing, cropping, or applying filters to high-resolution photos before upload.
Or think about parsing massive local data files like million-row CSVs.
Right. Are you still building giant trash compactors in your main thread for those tasks? Or is there a native API quietly sitting there, ready to take the load off your shoulders?
The wrench you need is probably already in your pocket. You just have to remember to reach for it.
It is a powerful shift in perspective. Until next time, keep exploring and keep trusting the platform.